It is time to discuss the SparseLand model and the prior that emerges from it. SparseLand is a generative model. That means that it provides an explanation about the signals by describing how they are created. This machine, marked as M, generates signals. Inside of it, the dictionary D of size n by m is stored in memory. When the button is pressed, a random sparse vector alpha is created. D times this alpha leads to the signal x at the output of this machine. This multiplication implies that the sparse vector alpha gathers a small subset of atoms from D to create x. So what is P of x for this model? In order to answer this, let's suggest a more specific description for the generation of alpha. We start by choosing k0 at random, the number of non-zeros that this vector will have. This could be done, for example, by preferring small values of k0 using this one-sided exponential probability, thus tending to sparsity. We proceed by choosing the actual non-zero values to use, for example being multivariate Gaussians, and their locations, which could be drawn at random uniformly. All this leads to a vector alpha, and when multiplied by d, it leads to a random x at the output. This path gives a clear and complete definition of P of x, even if it is not spelled out explicitly. Why are we so fascinated by the SparseLand model? Well, first of all, it is simple. Clearly, it is simple to describe, as we have just seen. However, more importantly, this model leads to simple explanation of signals believed to be linear combinations of few atoms from D. Alongside this simplicity comes a massive richness. Every possible support implies a specific low-dimensional Gaussian that may explain our signals. We have M choose k0 such supports, and this number is huge. Finally, we are excited about this model because it is closely related to many modeling ideas that have been floating around. And with this model, they are now purified, made more precise, and even generalized. How is this model related to some of the priors we have discussed? In order to answer this, let's assume for a minute that the dictionary D is a square and invertible matrix. In this case, the probability of a signal x is proportional to the exponent of minus lambda times the number of non-zeros in its representation alpha, as we have suggested above. Exploiting the relation d alpha equals x, we get that this is equivalent to the sparse transform-based prior we have already seen. However, SparseLand is in fact a generalization of earlier ideas because the dictionary D is overcomplete, and our prior works directly with L0 norm. A term often encountered when discussing the SparseLand model is union of subspaces. Let's explain it briefly. Suppose that we choose k specific atoms from D. All the signals relying on this set of atoms form a low-dimensional subspace. Well, there are m choose k such choices of subspaces, and every signal from our model, if created using k atoms, must belong to just one of these. Therefore, our model has a union of subspaces form. Now let's better define what we have referred to earlier as the pursuit task. Suppose that a noisy SparseLand signal is given to us where the noise is epsilon bounded. In an attempt to explain this signal, we desire to find which subspace originated it. We do so by searching the closest subspace to this signal. This task is completely equivalent to a search for the support in D that explains this signal, since the mapping between these subspaces and the supports is one-to-one. The hardness of this problem is evident due to the many supports that need to be checked. Therefore, the pursuit problem is nothing but a quest for the sparsest alpha that explains why, up to an epsilon error, this is a projection operation which aims to find the closest subspace in the model to our signal. SparseLand is closely related to the Gaussian mixture model, GMM. Here is a formal description of the probability density function of GMM. It is built as a weighted average of n Gaussians. Each of these Gaussians is characterized by the autocorrelation matrix QK, and these matrices are typically low rank to reflect the fact that these Gaussians are highly oriented. Observe that for simplicity we assume that all the Gaussians are centered on the origin. What is the relation to SparseLand? Well, every support in D leads to such a low-dimensional Gaussian. And thus, our model is a special kind of GMM, where n, the number of Gaussians in the mixture, is simply huge. And all these Gaussians draw their autocorrelations from the single matrix D.